Random variables are used to model situations where the outcome before the fact is uncertain. Put it another way, a random variable is a real number whose value is based on the random outcome of an experiment. Now, as we've talked about before, if we've got a list of every possible outcome for a given random variable, that's our sample space. This is the space that includes the outcome that eventually did take place, but also all the other outcomes that could have taken place but never did materialize. So the idea of a sample space puts the outcome that did happen in a larger context of all possible outcomes. Now, a random variable can either be discrete or continuous. Here's the definition. A discrete random variable takes on discrete values. In other words, values that are countable. For example, suppose you received 500 emails in a day. You're a particularly popular person. And let's let the random variable x be the number of new emails that you were able to reply to in that day. Then x can take on values either 0, 1, 2, all the way up to 500 if you were super productive. Now, certain discrete distributions appear frequently in real life, and so they've got their own special names. One of them we're particularly familiar with, which is the binomial distribution. For example, when we did the number of times that heads might appear out of 10 coin flips, that follows a binomial. Now, something slightly different in this sample. What if we looked at the number of flips needed to get to one head? Or maybe the number of cars that we need before we get to a single red car? Well, that follows a geometric distribution. The number of flips needed to get, say, n heads, where we pick any value for n, say 5, or maybe the number of cars that need to pass by to get n red cars, well, that's a negative binomial. So now instead of the number of heads needed to get 10 flips, this is the number of flips needed to get, say, 10 heads. There's also a limiting case of the binomial, where each actual event is rare. Almost like the number of times the coin lands neither heads nor tails. This is called a Poisson distribution, and it's always about unusual events. For example, maybe the number of defects on a semiconductor chip might follow a Poisson distribution. Well, we're going to talk about each of those distributions in detail today, but first, let's start with a simple discrete experiment. Here, we're going to flip a fair coin 3 times. Notice the possible outcomes: 3 heads, 3 tails, or everything in between. Now, each of those outcomes is equally likely, so they have a probability of 1/8. Let's let x be the number of times heads appears. X is a random variable, but what values can it take on? Well, let's look at our sample space. Here we see x can take on values of either 0, where there are no heads in the flip, 1, 2, or 3, meaning all 3 of our flips were heads. So discrete random variables then are defined by what we call their probability mass function, or the PMF. The PMF defines the values that the random variable can take on, and it tells us with what probabilities it can take on those. So back to our coin flipping experiment, the probability mass function for x is the following. The probability that x equals 0, meaning there were 0 heads in the 3 flips, is the probability of the event that we get 3 tails. So tails, 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 which happens 1/8 of the time, or 1 out of 8 of those outcomes. Likewise, the probability that x equals 1 means that of the 3 flips, 1 of them was a heads. And that occurs 3 different ways. Either a head on the first flip, heads on the second flip, or heads on the third flip. So that's 3 events out of 8. The probability that x equals 2, likewise, is 3 events. So 2 heads on the first flip, or a head, a first flip head and a third flip head, or the last two flips were heads. And lastly, what's the probability that x equals 3? Well, that's the event that all three flips were a head, which has probability 1/8. So this is our probability mass function for x. It describes the probabilities and assigns them to the event. Let's do a friendly wager. Let's suppose I'm going to be paid $1 for each head that appears in our coin flipping experiment. Now, if I'm only going to play this game one time, up to how much should I be willing to pay to play? Well, to help me decide, I might want to imagine if I played the game a large number of times and I looked at how much I won on average, that might give me an idea of how much I'd be willing to pay. Let's suppose I play n times. So in that case, on roughly 1/8 of those times, or 1/8 times n, I'm going to win $0 because I won't have any heads in that flip. Likewise, on roughly 3/8 of those times, I'm going to win $1. 3/8 of the time, I'll win $2, and 1/8 of the time, I'll win $3. My average winning over those n trials would be approximately the sum of each time I won $0, so 0 times the number of times I won 0, which would be n over 8, plus $1 times the number of times I won that, which would be 3 times n over 8, plus $2 times the number of times I won $2, 3n over 8, plus $3 times the number of times I won $3. And I'm averaging that, so I'm dividing that all by n to get the average. Well, notice those n's are going to cancel out really nicely for us. And what we're left with is 0 times 1/8 plus 1 times 3/8 plus 2 times 3/8 plus 3 times 1/8, or $1.50. So I should be willing to pay up to $1.50 to play this game in order to come out ahead on average. This is the idea of expected value. The expected value of a discrete random variable represents the long-run average, or the long-run value that that random variable can take on. It's also called the population mean because it's the value of the mean that we would get if we could enumerate the entire population of realizations of the random variable x. We write expected value of x, or E of x, as the sum of xi times the probability that x equals xi. Now, suppose if x heads come up, I win instead x squared dollars. Now how much should I be willing to pay? Well, here we're looking at the expected value of a function of x, in our case, x squared. Well, the expected value of a function, we just plug that into our formula. Remember, for E of x, we had the sum of x times the probability that x equals x. Here, we're going to just plug in the function h of x in place of x. So the expected value of h of x is the sum of h of xi times the probability that x equals xi. Let's do that for x squared. The expected value of x squared is going to be the sum of x squared times the probability that x equals x squared. Now here, the expected value is linear. In particular, if we had constants a and b, the expected value of ax plus b breaks down to a times the expected value of x plus b. The cool thing to pick out here is the following. When we take the expected value of a constant, it's just equal to that constant. And if we take the expected value of a constant times our random variable, that constant can come out of the expectation. And we can just multiply it by whatever our expected value is. Be careful though, because the expected value of a function is not necessarily the function of the expected value. So those aren't interchangeable. Now, we talked about the variance before, but now I want you to consider it in context of a random variable. By definition, we said the variance measures the spread of a random variable's distribution around its mean. Let's look at it for a discrete random variable. Here, the variance of x is going to be the expected value of x minus its mean. Okay, so x minus e of x, and we're going to square that. So similar to what we did before, except now we're looking at random variables. This breaks down to the sum over all I of xi minus the expected value of x squared times the probability that x equals x. The variance of the number of heads appearing after 3 coin flips can be calculated using this simplified equation. Expected value of x squared, which is 3, minus the mean squared, 1.5 squared, to get 0.75. The standard deviation of a random variable is going to be the square root of its variance. Now we can define a random variable always using its probability mass function. Here's an example. F of x equals 1 over 14 times x squared. But how do we know that this is a valid probability mass function? Well, because it sums to 1 over all possible values of x. In fact, if we plug in x equals 1, 2, and 3 into our probability mass function, here's what we get. F of 1 equals 1 over 14 times 1 squared, plus f of 2, 1 over 14 times 2 squared, plus f of 3, 1 over 14 times 3 squared, which should always add to 1. That tells us that the entire totality of the probability is going to be contained within that probability mass function. Now, there are certain classes of random variables that show up commonly in natural processes. We call these special discrete random variables, like the Bernoulli, the binomial, the geometric, the negative binomial, and the Poisson, among others. Suppose we've got an experiment where we have only 2 outcomes, something like maybe a success or failure, win or lose. Let's define x equal to 1 if a success occurs, and x equal to 0 if a failure occurs. Well, then we call x a Bernoulli random variable, where the probability that x equals 1 is equal to p, and the probability that x equals 0 is equal to 1 minus p, where p in this case is our probability of success. Well, the Bernoulli random variable is actually the building block of several of these distributions. Let's go back to our coin flipping experiment. We flipped a coin 3 times. Each flip had a probability of 1/2 coming up heads. The result of each flip was independent, and our random variable x counted the number of times out of 3 that heads appeared. When random variables show up like this, they're called binomial random variables. We say x is a binomial random variable with 2 parameters, n, which is the total number of flips, and p, the probability of a success, if it consists of a series of independent trials where each outcome is a Bernoulli random variable. So a success or failure, a heads or a tail. Now, the probability of success on each trial is a fixed value, which we call p. And x, this counts the number of successes out of n trials. In our coin flipping example, we would say that x follows a binomial random variable where n equals 3 and the probability of success equals 0.5. Now, the probability mass function of a binomial random variable can be written as follows. This is the probability that x equals some value k. Now, how do we solve this? First, let me draw your attention to p to the k times 1 minus p to the n minus k, because this is a little bit more intuitive. So remember, p is our probability of success, and we want to know what's the probability that we have k successes, that x equals k. Well, k successes means that we've had our success probability p k times. So we raise p to the kth power to indicate that we had k successes. Well, how many failures did we have? If our total equals n, then n minus k is going to tell us how many failures we had. And our failure probability is 1 minus p. So we take 1 minus p raise it to the n minus k, and that tells us how many failures we had. Now, this interesting n over k with parentheses, we call that the number of ways to choose k items from a set of n items. We call that n choose k. It's defined as n factorial over k factorial times n minus k factorial. So for example, if I've got 4 items and I want to know how many ways can I pick 2 items out of that 4, I can plug it into this formula to get 6 ways. Now the probability mass function for a binomial also has an expected value. Let's say you flip a coin 10 times and each coin has a probability of 1/2 getting heads. On average, how many heads do you expect to get? Well, probably 5 out of 10 is what we'd expect. Well, that's exactly how we calculate the expected value in this case. More formally, the expected value of x is going to be the sum, as k goes from 0 to n, of k times our binomial distribution. We can work that out, do a little math, and get n times p, which is what you would think of intuitively. Likewise, the variance of x works out to n times p times 1 minus p. And this variance is actually maximized at a p equal to 0.5. Now suppose we've got a series of Bernoulli trials, and we define x as the number of trials until the first success. Well, this is actually a geometric distribution. Here, our probability of success is p, also between 0 and 1. Let's look at our f of x for the geometric. Now, we've got how many failures? If x is the number of trials until the first success, that means I must have had x minus 1 failures before that success. So that's exactly what the geometric distribution tells you. I've got 1 minus p, which is my probability for failure, raised to the number of times that I failed, x minus 1. And on that last time, I succeeded with probability p raised to the first power. The expected value for the geometric distribution is 1 over p, and its variance is 1 minus p over p squared. Now let's suppose again we've got a series of Bernoulli trials. This time we're going to define x as the number of trials until we get to r successes. X now follows a negative binomial distribution with parameter p between 0 and 1 and r equal to 1, 2, 3, or so on. We can write the negative binomial probability mass function as follows. X minus 1, choose r minus 1, times 1 minus p to the x minus r times p to the r. Now let's dissect that a little bit. That first term is out of x minus 1, how many ways can we choose r minus 1, right? We've failed x minus 1 times, and so we're going to take our failure probability, 1 minus p, and raise it to the number of times we failed before we got to the rth success, so p to the r. Now, here's a funny distribution, the Poisson, that might look a little weird at first. It has a parameter lambda, and here's what that probability mass function looks like. The probability that x equals k is equal to lambda to the k, e to the minus lambda, all over k factorial, for k equal to 0, 1, 2, and so on. Now the Poisson has expected value and variance both equal to lambda, so it's easy to remember. All right, I know you might think to yourself, what on earth follows a Poisson distribution? Well, surprisingly, it actually shows up pretty frequently, and it looks at events that occur very rarely, like the number of typos on a page in a textbook, the number of deaths due to horse kick in the Prussian army, who knew? Or even the number of customers that arrive at a grocery store line to check out over an hour. Now, we've seen several discrete distributions, but that's not the only type of random variable that we're going to look at. A continuous random variable is a random variable that now is going to take on values over an entire interval. For example, what if we wanted to look at the position of a defect along a length of wire? That would be a uniform distribution. Or maybe the time between emissions of alpha particles in radioactive decay. That is exponential. Or even the droplet size of a pesticide that's sprayed through some nozzle. It's a normal distribution. Let's consider a 4-meter length of wire that has a defect somewhere on it, and assume that the defect is equally likely to be located anywhere along the wire. What do you think the probability is that the defect is located in the first meter? If it's 4 meters, first meter, maybe 25%, right? 1 out of 4. How many possible outcomes do you think are in that first meter? It's a little more complicated. There are lots of ways that could occur. Here's another question. What's the probability that is located precisely at 3.286438 meters? Well, if x is a continuous random variable, taking on values on an interval, the probability that is equal to a particular point is equal to 0. So in this case, the probability that our defect laid at 3.286438 meters has 0 probability. Otherwise, if we added up the probabilities over the entire interval, the total would include 1 if we could get probability at a single point. So a continuous random variable doesn't have a probability mass function, which associates a probability to each value. Instead, what we get is a probability that is spread over intervals. And we call this the probability density function, or the PDF. Now, the density function for a random variable speaks to the frequency of the outcome, the random variable x, over an interval. Now, density functions for continuous random variables, they don't correspond to the probability. In other words, f of x is not equal to the probability that x equals little x. You can look at a histogram to kind of get the shape of a continuous distribution. Instead, it takes on values over a real interval. So the position of defect over a wire has constant probability. The time you need to wait for emissions of 10 alpha particles might be a sum of exponential distributions, known as the gamma distribution. The PDF, f of x, in the continuous case, is defined as follows. It's the probability that x is between a and b, so located between the intervals a to b. We get that by integrating over the function f of x, so the integral from a to b of f of x dx. Here's an example. We've got a plot of a probability density function, and we want to know what's the probability that x is between a and b, where a and b are 2 and 3.5. So we would actually integrate over that area to get that associated probability. The cumulative distribution function, or the CDF, is the probability that x is less than or equal to some value, say y. Imagine that we've taken our probability density function and we've added it up until we get to the point y. In this case, we find that by integrating from minus infinity up to y of our probability density function, our PDF. The expected value looks similar as it did in the discrete case, except now instead of multiplying x times p of x and summing those, we're going to integrate over that product. So for the expected value, we get x times f of x dx, and we integrate that over all possible values from minus infinity to infinity. The expected value of a function also looks similar. Expected value of h of x equals the integral from minus infinity to infinity of h of x times f of x dx. And for our variance, those sums have become integrals. The variance of x, which is the expected value of x minus its mean squared, can be written as now the integral of x minus its mean squared times f of x dx. But notice that it breaks down to that familiar formula that we're used to. Now, continuous distributions have great properties. In fact, f of x is going to be greater than or equal to 0 for all probabilities over the interval. Otherwise, we could have negative probabilities. Secondly, the integral over all possible values has to equal 1. We talked about this when we talked about sample size, how our sample size has probability 1. Well, for our density function, when we integrate over it, we should get the total probability, which is 1. And lastly, f has to be integrable over our entire sample space. So we can't have a function that lives in our space where we're not able to integrate that function within the space. We have to always be able to integrate it. Let's talk about some particular distributions that are continuous and amazing. First is the uniform. This distribution tells us the values on the real interval from a to b that are equally likely to arise. We write that as x is uniform on the interval from a to b, where a is less than or equal to x, and x is less than or equal to b. So for example, maybe we talked about the location of defects on a wire, or it could be the time until the next regularly scheduled train arrives. Those all follow a uniform distribution, which you can see graphed here. Now, since x is uniform, f of x is equal to a constant, and we need the area under the curve to integrate to 1. So when we integrate that, the constant that comes up is 1 over b minus a. This is our probability density function for the uniform distribution. Now suppose x is uniform on the interval from a to b. What's the probability that x is less than or equal to c, where c is some number that lives between a and b? Well, in this case, we're looking at the area of the curve between c and a. We calculate that probability by integrating from a to c, 1 over b minus a dx, which equals c minus a over b minus a. For example, if x is uniform on the interval from 1 to 5, the probability that we're less than 3.5 would be 3.5 minus 1 over 5 minus 1, or 2.5 over 4. Suppose x is uniform AB again. What's the probability that x is between two numbers, c and d, where c and d are between a and b? So now we want to know the probability that x is inside c and d on the interval from a to b. Here we're going to integrate over c to d times our probability density function, 1 over b minus a, to get d minus c over b minus a. Again, if x is uniform 1, 5, the probability that x is between 1.5 and 3.5 is the difference, 3.5 minus 1.5 over 5 minus 1, or 2/4, which is 1/2. Other properties of the uniform distribution. We've talked about the density function, which is 1 over b minus a. But what about its mean? So in this case, when we calculate the mean of a uniform distribution, see we get a plus b over 2, which kind of makes sense visually. If my uniform distribution is uniformly distributed between a and b, the average is just going to be the center of those, which is a plus b over 2. The variance, not so intuitive, but it's b minus a squared over 12. And we can get there from the formulas that we've learned already. The exponential distribution is another common continuous distribution that we see in real life. It's defined as follows: f of x equals lambda e to the minus lambda x for x greater than 0. It has an expected value of 1 over lambda and a variance of 1 over lambda squared. Now, you often see exponential distributions when we model the time between events that occur at some rate, say lambda. Now, here's a common pitfall that we often see in continuous random variables. If, say, there's only 2 possible outcomes, you don't know which one is true. Instinctively, people think to assign each of them a probability of 1/2. In fact, most probabilities that are binary can be anything from 0 to 1. So for example, if the outcome of interest is has cancer or doesn't have cancer, the probabilities of having cancer in most cases are much less than 1/2. The number of possible outcomes in an experiment doesn't necessarily say anything about the probability of those outcomes.